Hi everyone, welcome back to chemistry. In this video, we're going to start our 5th study guide, which is all about something called the mole. In order to understand what the mole is, I first want to just talk about the grocery store. So today I went to the grocery store and I had to stock up on some eggs. And if you eat eggs, or you just know people who do, or your family does, you know that usually when you go to the grocery store and you buy eggs, they come in packs of 12. And we call that pack of 12 or 12 eggs, we call that a dozen. So a dozen eggs is 12 eggs. But we can also use the term dozen to describe 12 of anything, right? Or to count 12 of anything. So you can have, if you have a dozen eggs, you have 12 eggs. If you have a dozen pencils, you have 12 pencils. If you have a dozen apples, you have 12 apples. And so on. So a dozen means 12 of whatever item you're counting. Likewise, if you have a ream of paper, you have 500 sheets of paper. If you have a gross of pencils, you have 144 pencils. So these are like common terms that we can use to count the number of items that we have of various items. So the mole is actually, some people call it the chemist's dozen. And you don't have to write this down, but if it helps, you're welcome to. So some people call it the chemist's dozen. And that's because we use the mole in chemistry to count particles, or the number of particles. And we'll talk about more specifically what I mean when I say particles. But it's another way of counting the number of things that we have. And it's a special one for chemistry. So if say you're in lab and you measure out 5 grams of NaCl in a weigh boat, right? And you're using your analytical balance and you've got 5 grams of that substance, and you wanted to know, hey, in this 5 grams of NaCl, my table salt, how much of that is sodium ions? How much of my sodium chloride sample that I have is just sodium ions? Well, there's actually a way that you can determine that. And normally it would be really, really difficult just using regular units. Because in 5 grams of your substance, which is relatively a small amount-ish, right? You'd have tons and tons of those ions, right? Remember, those particles are so tiny. So there was an Italian physicist named Avogadro who kind of came up with this idea of the mole. And it was a way to be able to actually count these tiny particles, atoms, molecules, ions, these tiny things in chemistry. Okay, so we would actually have a way to quantify, hey, how many of these things do I actually have? So just like a dozen is 12 eggs, 1 mole is 6.02 times 10 to the 23rd of that thing. Okay, and sometimes you'll actually see 6.022 times 10 to the 23rd. Actually, let me make that a little clearer. 6.022 times 10 to the 23rd. That's actually what I'm more familiar with, but either way is fine. So whenever you have a mole of anything, you have 6.022 times 10 to the 23rd of that thing. That's a really big number, right? And that number is called Avogadro's number. And the reason that we represent it like this in scientific notation is, just remember, if you think back to the beginning of the quarter, we can use scientific notation to represent these really large numbers. And why is this number so large? Well, remember that atoms, molecules, ions, these are really small particles. So we'd have a lot of them, and that's why that number is so big. And that number, again, is called Avogadro's number. So this whole thing in blue that I have here, or sorry, technically just the number part, that is Avogadro's number, okay? So we can use Avogadro's number to count, and the mole, right? We can use this equality to count how many of those particles. So 1 mole of your item is 6.022 times 10 to the 23rd items. So in chemistry, we often use the mole to count the number of atoms. But remember, a mole of anything, a mole of pencils is 6.022 times 10 to the 23rd pencils. A mole of cats is 6.022 times 10 to the 23rd cats. A mole of apples is 6.022 times 10 to the 23rd apples. 1 mole of anything is 6.022 times 10 to the 23rd of that thing, okay? But a lot of times in chemistry, we want to count atoms specifically. So here are just some examples of how you might see that done, right? So a mole of some element is 6.022 times 10 to the 23rd atoms of that element. A mole of carbon is 6.022 times 10 to the 23rd atoms of carbon. A mole of sodium is 6.022 times 10 to the 23rd atoms of sodium, okay? So 1 mole is that many of that thing. I hope that makes sense. So just like we can use any equality to create conversion factors, we can do the same thing with the mole and Avogadro's number. So if a mole equals 6.022 times 10 to the 23rd particles, then we can split that equality, right? This is our equality because it has that equal sign. We can split that up into 2 conversion factors. Just like we can split up, 1,000 milligrams is 1 gram into 2 different conversion factors like this. I guess I should write it like this first. Okay, so you can split that up into conversion factors, and you can do the same thing with Avogadro's number. So there you've got your different conversion factors where you have a mole on top and 6.022 times 10 to the 23rd particles on the bottom, and then vice versa. All right, and one of the ways that this is really useful in chemistry is to convert moles of some substance to any kind of particle of that substance. So say we wanted to know, for instance, this example here, how many CO2 molecules are in 0.500 moles of CO2. So determining, okay, if I have this many moles of my substance, how many particles, molecules, atoms, ions, whatever, are in that amount of moles, okay? So let's go ahead and try this example together. So how many CO2 molecules are in 0.500 moles of CO2? Let's zoom out just a little bit here. So for all of these kind of unit conversion or dimensional analysis problems, I always start them off the same way. I ask, what am I given and where do I want to get to? What am I given and what's my goal? So in this example, I'm told that I have 0.500 moles. This is a common abbreviation for moles. So you'll see MOLS. It really only gets rid of that E in there, but it still helps a little bit when you're writing this out a lot, so you can write it like that. Of CO2. So sometimes you'll also see that I drop the of right here. You don't have to write of. It's just kind of assumed if you just write whatever you have next to it. But you always, always, always want to write what you have next to it. And I was a little bit lenient on this when we were first doing unit conversions, but now that we're actually going to be using the mole, I want you to get into the habit of saying what, moles of what, atoms of what, molecules of what, because we'll be doing conversions that involve several different types of compounds or substances, okay? So just get in that habit. All right, so 0.500 moles of CO2 is what I'm given. So that's the first thing I write down, and it's going to be the first kind of train track in my conversion problem, okay? And now I want to get to CO2 molecules. So I'm given this number, right? And I want to get to here. Well, what unit or conversion factor do I have that connects these two things? Well, let's look up here. 1 mole of something is 6.022 times 10 to the 23rd something. So let's see. What if we use Avogadro's number to connect these two things? And that's exactly what we're going to do. So if we know in 1 mole of something, anything, so let's say 1 mole of CO2, 1 mole of CO2, we have how many? 6.022 times 10 to the 23rd, what? Right, atoms, molecules, ions, any of those types of particles, cats, dogs. 1 mole of anything is 6.022 times 10 to the 23rd of that thing. So if I have a mole of CO2 and I'm looking for molecules of CO2, then I'm going to put molecules here, right? Because 1 mole of CO2 is that many molecules of CO2. It's our unit. It's just like a dozen. A dozen of anything is 12 of that thing. Okay, so this is legal. It's perfectly legal. I know it seems weird. So if I want to cancel out moles and end up with molecules, what number needs to go on the bottom here? Do I need Avogadro's number or this one? Yeah, I need moles on the bottom. So 1 mole of CO2. So this stands for moles as well. It's just the singular version. So instead of plural, right? Moles versus mole. Anyway, so 1 mole of CO2 is 6.022 times 10 to the 23rd. Let me give myself a little more room here. Molecules CO2. Okay, and now I can actually cancel out those moles, right? So I'm canceling out my moles there and my moles here. And what am I left with? Yeah, molecules of CO2, which is exactly what I wanted, right? That's exactly where I wanted to get. So how did I get there? Well, I said if I know how many moles of my thing I have, and I know in 1 mole there's always 6.022 times 10 to the 23rd. You're probably so tired of me saying that number. Then I know that I have that many of that thing, right? All right, so let's go ahead and carry out this calculation. So let me get my calculator. Okay, one more quick note. This number or this equality is considered exact. Okay, it's considered an exact value. So what does that mean? When you are trying to figure out how many sig figs to report in your final answer, you're not going to look at this conversion factor here, okay? Because it's considered an exact value. It's not considered a measured value. It's not something that we're measuring in lab. It's considered an exact quantity. So the only number that you're gonna look for, remember, are measured values. So something like this, right? 0.500 moles of CO2. Someone measured that in a lab and said, hey, that's how many moles of CO2 I have, okay? So we're gonna use that to determine how many sig figs we have. And it looks like here we have 3 sig figs, right? We count these 2 zeros because they come after, there's a decimal point in that number. So they're significant. So we should have 3 sig figs over here. All right, so now I have 3 sig figs in my final answer, and we've determined how many molecules of CO2. Final check. Should we have this big of a number of molecules of CO2? Why is it okay that we have such a large number? Yeah, molecules are really, really tiny. So even though our sample is pretty small, right? We've got 0.5 moles. That's okay. We should expect a large number because they're so tiny, okay? So if you plug this into your calculator and you got some number that was really small, like say you got like 5 molecules of CO2, that's way too tiny. You did something wrong, okay? Because you should have a very large number of molecules, okay? All right, let's keep moving on. So what I want you to do is pause the video and try this learning check out. You're going to try to figure out how many atoms are in 2.0 moles of aluminum. Okay, and you've got some options there. Pause the video, try it out. All right, so this is what I'm given, right? So this is what's going to go on the top left of my conversion or of my dimensional analysis problem. So I got 2.0 moles of aluminum. All right, so I want to get to atoms. That's my goal. I want to get to atoms. What connects moles and atoms? What connects moles and atoms? What connects these two things? Yeah, Avogadro's number connects those two things. So I know I'm going to be using Avogadro's number, which is what? Yeah, 6.022 times 10 to the 23rd. 6.022 times 10 to the 23rd. I'm just going to, you're going to get so tired of me saying that. So what goes on the bottom? Moles or atoms? Yeah, moles. How many moles? 1 mole. 1 mole of aluminum. Why did I choose 1? I only know the conversion factor between 1 mole and 6.022 times 10 to the 23rd. Okay, that's the only conversion factor I know. So we'll do 6.022 times 10 to the 23rd. In the top, what is it? Atoms of, aluminum. Okay, just like before, we can cancel out these moles. And now we're left with atoms of aluminum. So what do we get out? Let's see. So 2 times 6.022 times 10 to the 23rd is 1.2044 times 10 to the 24th atoms of aluminum. And accounting for sig figs, we're going to round that to 1.2 times 10 to the 24th atoms of aluminum. That's my final answer. Let's see. All right, so we've seen that the subscripts in a chemical formula of a compound actually show the number of atoms of each type of element are in that compound. So for instance, in aspirin here, we can look at that and we can say, well, there are 9 carbon atoms in aspirin. There are 8 hydrogen atoms and 4 oxygen atoms, right? Those are what those subscripts mean. Well, we can also use those subscripts to determine the number of moles in that compound. Kind of weird, I know. So just like this 9 shows us that we have 9 atoms of carbon, it also shows us that we have 9 moles of carbon. 9 moles of carbon. Really weird. This 8 can mean we have 8 atoms of hydrogen, and it does. But it also means we have 8 moles of hydrogen. This 4 means we have 4 atoms of oxygen, but it also means we have 4 moles of oxygen. Okay, so just like we can write conversion factors to convert between, moles of a substance to molecules of a substance or atoms or ions of that substance, we can also use it to write conversion factors for moles of each element within 1 mole of a compound. So what do I mean by that? So it's a little weird, but in this aspirin, in 1 mole of aspirin, there are actually 9 moles of carbon. In 1 mole of aspirin, we have 8 moles of hydrogen. In 1 mole of aspirin, we have 4 moles of oxygen. And you can actually make a conversion factor for each of those relationships. So you can say, okay, 9 moles of carbon can go on the top, and 1 mole of aspirin can go on the bottom. What is that saying? It's saying that for every 1 mole of aspirin, there are 9 moles of carbon within it. I know that's weird. It's like, how can there be 9 moles of something and 1 mole of something? You just have to kind of accept the weirdness a little bit. So again, like as always, you can flip this whichever way you want, right? there's also 8 moles of hydrogen per every 1 mole of aspirin and 4 moles of oxygen per every 1 mole of aspirin. And again, you can use these conversion factors whichever way you want in equations. Okay, so let's do this learning check together. So how many atoms of oxygen are in 0.150 moles of aspirin? So we are given this number, 0.150 moles of aspirin, and we want to get to atoms. Do we want to get to atoms of aspirin? No, we want to get to atoms of oxygen. So it's a little bit different. So this is our goal. All right, so just as usual, let's break this down into steps. So we'll start with what we're given. Moles of C9H8O4. All right. So I want to get from moles of aspirin to atoms of oxygen. So one of the things I need to know is how many moles of oxygen are in a mole of aspirin. So let's see. If we have C9H8O4, how many moles of oxygen are in that aspirin molecule? Yeah, 4. How did I know that? Well, there's this little 4 right there. And that means either we have 4 atoms of oxygen per every aspirin molecule, or also we have 4 moles of oxygen per every 1 mole of our aspirin as a whole. Okay, so we're going to put 1 mole of C9H8O4 on the bottom. And what goes on the top? Yeah, 4 moles of oxygen. Okay, 4 moles of oxygen. So now we can cancel out those moles of aspirin, right? And now we're in moles of oxygen, which is great because I eventually want to just get to atoms of oxygen, atoms of just oxygen. Okay, so now we have moles of oxygen. We want to get to atoms of oxygen. So I'm going to go ahead and put atoms of oxygen on the top there. Now, what goes on the bottom to cancel out those moles? Yeah, moles of oxygen. Do we have something that links moles and atoms? Yeah, we do. It's Avogadro's number, right? So let's scoot that over a little bit. So Avogadro's number says that for 1 mole, 1 mole of oxygen, there are 6.022 times 10 to the 23rd atoms of oxygen. And now we can cancel out those moles. Yeah. All right, so let's check with this calculation. So just as before, right, we're gonna say this number times this number times this number. Okay, and then divide by everything on the bottom, but that's just 1 times 1, which is just 1. So let's look at our solution. And it looks like we set it up correctly, and we would get 3.61 times 10 to the 23rd atoms of oxygen. And the reason we have 3 sig figs here is because we've got 3 here. Yeah, kind of nifty, right? So just to kind of summarize, we said, all right, in 1 mole of aspirin, I have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. And I know that from the subscripts. So I can use those subscripts to write a conversion factor that shows, hey, how many moles of this specific element that I'm looking for are in my aspirin molecule. Well, I know now that there's 4 moles of oxygen per every 1 mole of my aspirin. And so then I can actually just use Avogadro's number in order to get to atoms of oxygen, which was my final goal. All right, I know this is really tricky at first. If you have any questions, let me know. We'll keep plugging along, and I'll see you in the next video.